Okay, welcome everyone. Thank you all for coming to this talk. It's a real pleasure to be here. It's my first time in Devox, Poland, and it's what an awesome venue. So today we're going to be talking about two subjects which I think are pretty interesting. The building business systems, really based on services, and this other idea of stream processing. Particularly using a kind of retentive log. And whilst these two things seem in many ways quite different, hopefully today you'll see that they're two things that we can blend together to build potentially significantly better systems. So my name's Ben Stopford. I work at this company called Confluent. Anyone heard of Confluent? I've got a few. So we're the company that sits behind Apache Kafka. We're set up by the founders of the people who wrote Kafka originally at LinkedIn. And we'll be talking a little bit about Kafka and K-streams, although a lot of these principles are a little bit more generic. So this is me. I work as an engineer. That's my day job. Kind of recently been working on the replication protocol, automatic data balancing, some of the sort of internals of the distributed log part. And previously I worked at ThoughtWorks and some other institutions, and I come from the UK. So I wanted to start by reflecting a little bit on services, or at least why we build services. For a lot of people, services are about splitting a monolith. That's the way that a lot of people come to them. That makes a lot of sense. Right? You should always build the simplest thing that you can build, and often when you're bootstrapping a new application or a new company, you want to start with the simplest thing. You want to start with something that's monolithic. And then often you need to scale that. So a lot of service architectures are actually built out of necessity. They are things which evolve. And that's actually a good thing. Evolving an architecture is a good thing. In fact, I would actually define the definition of a good architecture as being something which you are able to evolve. That's the kind of the property that I look for. But if there's one thing that really defines a microservice architecture, and actually SOA before it, it's this idea of autonomy. So what this really means is, if you're building a service, if you're building the orders service, you want to be able to get a requirement from your users. They might say, we want you to add this new feature. You need to be able to develop that with a degree of isolation. Right? You need the ability to be able to deploy that service independently. You need the ability to get at the pieces of information that you need to implement that particular feature. You don't want to be too encumbered by the services that are around you. So this property is quite important, this idea of services being independently deployable. This is kind of really where services get their value. And this value comes from scaling. Right? It gives us an ability to scale. And this is, whilst this to some extent will allow you to scale to, let's say, petabytes of data or millions of users, what it really allows you to do, or one of the most useful features of scaling in this regard, is scaling in people terms. So if you try to scale a monolith, it's totally possible. Facebook did it for a long time. Etsy still, if you listen to the guys from Etsy, they'll still talk. They still talk about the benefits of a monolith. But it is typically quite hard to scale in people terms. And actually, companies themselves tend to be collections of applications, often not deliberately designed, but they always are. Right? Which, if you work at a company that has maybe more than 1,000 people, you'll have several hundred applications potentially. And they're all going to connect together in some way or other, even if it's just passing files around or polling databases. They also need to work together in some degree, and often the way that they're interconnected ends up being something of an afterthought. So the kind of FTP file transfers, maybe enterprise messaging, that sort of thing. So microservices and SOA are really patterns that allow us to reimagine multi-team architectures in a way that actually is sympathetic to getting a single job done, working cohesively together. So when we do this, In sort of traditional development scenario, we'll get a requirement from a user and we'll go, right, we're going to build a new application and we'll work out how to build it and we'll get a database and we'll pick the language of choice and we'll build our little application. And it tends to be built in isolation. The thing about services is they kind of force our head up and they make us think about a wider ecosystem. So your place in the wider ecosystem, that external world, is actually very important. It becomes something that you design for, as well as the internal world of your particular service where you alone reign king. So the external world is really something that we want to design for, but we also want this idea of independence. So it's this independence which allows us to scale whilst still getting things done. But this idea of independence comes at a cost. And this is somewhat intuitive from the perspective of thinking about problems that we see every day. So for example, let's take a simple sort of object-oriented modeling problem. We know that if we have two objects, over here we have an orders object on the left and a statement object on the right. And the orders object has some state and some behavior. And we all know our good OO principles will teach us to encapsulate that state and behavior. We'll get a nice, clean interface. In this case, it's get all open orders. And we'll hide that state and behavior from things which are calling us. And the reason we do this is to get loose coupling. Loose coupling basically allows us to change. It protects us against future change. And this works really well in a monolithic application because when the business comes to you and says, I would like you to add this new feature, and this feature actually involves both the orders object and the statement object changing, we can make those changes to both sides. We can redeploy the application. It's all pretty simple. Maybe we make some changes to the database. In a services world, it's not quite so simple. We typically don't have a shared database. We also don't have these independent release cycles. So if we have a change which is going to cross-cut both of these services, we have to do some sort of scheduling. We have to get one team to make a change and then the other team to make a change and kind of schedule these two things to go out together in some well-defined order. So that's pretty easy, actually, for two services. But if you've got, 20 or 30 different services, this becomes a real problem. So services actually work best where they have this idea of an isolated requirements which are isolated inside a single bounded context. SSO is a really good example of this. So the wonderful thing about something like a single sign-on service is it has this very simple interface, right? Authorize. And there's basically no requirement which your business is going to throw at you which is going to make that interface change. It's going to stay there probably forever unchanged. It lives in this very tightly bounded context. So it's like a really good example of a service. The problem is that the services that we build, business services, tend to be a little bit different. Business services don't have such clean abstractions. It's just not kind of the way the world works. So if we consider data, for example, imagine we have like an online retail example, a retail website. The data sets of customers, orders, the product catalog, these things will proliferate through many of our services. Our services will need access to these data sets to do their jobs. So the point really is, the authorization example, that's nice, tightly bounded context over here. But these guys, much more intertwined. So the reality of building business services is their futures are much more tightly intertwined. So when we start to think about these concepts and blend them with data, some interesting things happen. So we need this idea of encapsulation, right, to retain loose coupling. But we also need the freedoms to get access to the various different data sets which define what our company does. But the interesting thing about data systems is data systems have little to do with encapsulation. if you think of like the traditional relational database, it is effectively the antithesis of encapsulation. A database does a whole variety of things to actually amplify the data that it holds. It can contort it into this whole range of wonderful different shapes for you. It's literally the opposite of encapsulation. It's an amplifying interface. So if we have a service, we have data on the inside, over on the left, and we'll actually encapsulate so that the data on the outside, the data that we expose, is as small as possible. Whereas data systems, databases, etc., actually provide these amplifying interfaces. And they actually also provide often shared mutable state. So we kind of end up with this dichotomy. Data systems are really about exposing data. They're about contorting it into a bunch of different ways and getting you the answer to a question that you need today. Where services are really about encapsulating, trying to protect your service against future change. So when we think about this in the context of microservices, I keep doing that. Who's heard this piece of advice? Microservices shouldn't share a database. Show of hands. So my ex-colleague Sam Newman's here, and he basically has written a book which is sort of trying to push people to do this. And it makes a lot of sense. The reason it makes a lot of sense is that there is nothing which is a richer point of coupling than a database. Other than having this hugely amplifying interface, it's also shared mutable state, and we've been trying to get rid of shared mutable state from our applications for years. And we kind of know this intuitively, right? So when we build service applications, we typically don't share a database. We'll have a strategy for getting around this problem. In fact, we typically have two strategies. Or one, we will use one of two different strategies to get around this particular problem. The first one is that we have our data we create a data service, we have our data in a database, and we'll wrap it with an interface. One of two things happens next. The first thing that happens is we end up gradually growing this interface over time. And you've probably seen this. So over time, we sort of have this interface, and we add a variety of different things, different methods for getting more specific data from this data service. And the amount of data on the outside just continues to grow. Or maybe we just add more and more and more interfaces or more and more methods to the interface. So maybe we come back a couple of years later. I'm sure this is going to resonate with some of you. And we end up with this massive long list, and these methods get longer and longer, and they have more and more specific things written on the end of them, to the point that we kind of end up building these strange kooky databases anyway. We've just wrapped them in a kind of little bespoke language of our own. And actually, as data volumes increase, this amplifies this problem because these data services have got more work to do. So that's kind of the first way it goes, which basically end up building slightly strange kooky databases, just wrapped in an interface that we created. The other way this kind of falls out is that we end up working out ways to move entire data sets from service to service. And the reason this tends to happen is that process of constantly getting all of these different methods added to our data service takes time, right? The data service has to change. It's got an independent deployment cycle, so you have to wait for it. So you kind of get hacked off, and you need to get a requirement implemented. If there's one thing we're really good at as developers, it's if we've got to hit a deadline, we're going to hit that deadline pretty much whichever way with whatever mechanism we have available to us. So we end up literally just working out a way just to get access to the data so that we can implement the requirement we need to do for our business. Copy the data internally. But this leads to a different problem. And this is actually the pain which is seen in a lot of very big organizations. If you work for a Fortune 500 company, you will see this a lot. So the problem is that we end up with data copied to a whole variety of different services and a whole variety of different databases where it's kind of mutated in place, and it diverges. So the core facts of your business end up being just damaged over time. And this is a very difficult problem to solve. So the more mutable copies you have, the more data will diverge over time. So we kind of end up in this cycle. We start over on the left, we have a new system, we draw a beautiful picture on a whiteboard, and it all looks really sexy. And then as things start to grow, we'll start off by growing the contracts of our data services. And at some point, we might end up creating something that's literally just too complicated for us to manage, in which case we'll go back and redesign. Or alternatively, we take this other path where we just work out a way of distributing data to a whole variety of different services, in which case we end up with this data divergence problem. So the point here really is that there are three fundamental forces. There's accessibility, our ability to iterate, there's coupling, this need to sort of retain independence so that we can change. And then there's this problem of data divergence. And these forces are actually fundamental. There's not much you can do about them. All you can actually do is pick a different point on this kind of trade-off curve. And that's really what I wanted to talk about today. So is there a better way of doing this? So the first step to take is to think about building on a backbone of events. And event-driven models have a few advantages. The most notable one is they allow us to decouple different parts of the system through asynchronicity and through a broker. And the way we do this is typically with an event-driven architecture, so event-driven services. I'm not going to go into this into too much detail. There's lots of information on the internet. People have been building event-driven architectures for decades. But effectively, in this kind of flow, you have, in this case, 3 services, and we can move a business flow through a variety of different states simply by exchanging events across an asynchronous platform. So we start with something that's asynchronous, and then on top of that, we blend in areas of queries or commands, synchronous protocols where we need to. Because we need these. If you're implementing a GUI and you need to find out, how many items the user has in their shopping basket, you need a request response-based protocol. You might actually build that on something that's asynchronous, but that's a different point. So we sort of start with something that's asynchronous as a backbone and layer the synchronous protocols on top. Step 2 is to make data on the outside a first-class citizen. And this is the one that really addresses what I think is the kind of gaping hole in the way we build services today, which is that we don't have a very good way of dealing with data. We actually have to. We have to think about data on the outside. We have to think about the data that our services share and actually design for it. The problem is today we don't have a great way of doing this. So one way to do this is with a streaming platform. And in this instance, we're going to have stateful streams at the center, and we have a set of services which sit around this, following this kind of event-driven architecture. And we're actually going to embed stream processing into each of these services as a mechanism for slicing and dicing data. And this gives us a very different type of solution. You could do this with a bunch of different technologies. Kafka is by far the most mature, I would say. It's also the only one that I really know. So I will be talking about Kafka in this context. But Kafka is a streaming platform. And what that means is at the core is a distributed log. And it has a streaming engine, which is just an API over that distributed log, some connectors that get data in and out, and then producers and consumers, which is just a simpler interface for just putting data in and taking it out. So the log itself, so the one kind of key takeaway, who uses Kafka today? Anyone? We've got a few. So Who's used a messaging system? Okay, so a lot more. So Kafka is effectively, you can think of it as a type of messaging system. The main difference between it and something like, let's say, I don't know, TIBCO or RabbitMQ is its ability to scale. So it's a distributed system by default. You can put massive pipes of data through it if you want to, like literally petabytes of data through it. So, and the reason for this is that it's linearly scalable at each tier. So if you've got a tier which is adding data at the top, that can scale out linearly. The broker in the middle, that can also scale out linearly, as can anything which is consuming. So we can literally put, terabytes of data per second through this type of architecture without it being a problem. Has some other interesting properties, though, which are useful from the perspective of services. We get fault tolerance built in. That's kind of a given. If a machine goes pop, whether it's a Kafka broker or whether it's one of your services, it will just like naturally rebalance, and it sorts all those kind of problems out. And the next release has transactions. The most useful part of that is actually the fact that, from a services perspective, it's the fact that you don't have to deal with idempotence anymore. Idempotence isn't that difficult, but it's kind of annoying, and it's really easy to get wrong. So it kind of solves that problem. But the one that I really want to dwell on today is kind of these two. It's the fact that the data model, the data structure that Kafka uses is a log. And what that means is you can keep data in it long term. It has this very simple interface where you basically just stream data from an offset. But it's effectively O of 1 for write and O of 1 for read, so you can leave very large data sets in there and replay them. And you also have this tool for making a log look like a table by deduplicating it with a primary key. It's just like another feature which allows you to imagine a table inside a log. So the important point here really is that this is an interesting place to keep this data on the outside, this data which our services exchange. Right? Normally, services just talk to one another because they kind of want to get something from the guy over here. But in this instance, we're actually using events, and we're going to make those events something we're going to hold on to. We're actually going to make them the data set of our system. It's a place to keep data on the outside. So if we work in retail, let's say, these events, the order events, every time an order is created, the customer events, every time a customer updates his details, whilst these fly from services to service, we're also going to retain them as a canonical set of that information so that any new service can just refer to them if it needs to. So these services can effectively just cache views of this backing data store. So that seems kind of interesting. Next thing we do is we add stream processing. And the reason stream processing is useful is that Kafka's interface is relatively simple. It's like reset to a point, maybe it's 0, but you reset to some point and then you just get messages in the order that they were added to this particular topic. But stream processing adds something useful on top. It adds the ability to basically slice and dice these data sets. But interestingly, inside your service, inside your process boundary. So stream processing at a very high level is just like a machine which we can use to combine different streams of events. So just like these boxes are coming in on these conveyor belts, we have like a machine. We tell the machine to do something. I would like something new from these various different events, please. And it just pops these things out the other side. So it's a very simple idea. When you use it, it looks a lot like a database. Same kind of features as a database. You can create a view. So you might map something to your internal domain model. You can join different streams together. You can add predicates to filter. You can aggregate, etc. But importantly, as I said, you're embedding all of this inside your service. You don't have to, you could run it independently, but by default, it's just a library, right? So it's just a library, you just interact with it, and it gives you this ability to join these various different streams. So here we might be joining together, let's say, orders and payments and performing some business calculation. We might also store some data back. That's part of stateful stream processing. So it gives us this ability to add a view, an index on top of these shared streams. So stateful stream processing is actually an extension of traditional stream processing. And that extension basically adds one thing. It adds statefulness, which we can think of as really as adding tables. So in any stream processing engine, you'll be handling events which are just sent to you. Messages are constantly being streamed at you. In stateful stream processing, you're going to accumulate that data actually inside a small database, which is part of the API. So you're actually going to overflow this stuff onto disk. And there are two kind of primitives in stateful stream processing. As data comes in, there's streams and tables. So a stream, they're actually basically the same thing. It's just about retention. So a stream is data's flying at you, and you will retain it for some period of time. So I might say, this is an infinite stream, and I'm going to retain 2 weeks' worth of information. A table is the same thing, but when I retain my data, I'm going to retain it with a key, and I'm actually going to hold the whole data set. So for example, if I have a table of customer information keyed by the customer ID, I would actually end up with all of the customers. So whenever a customer changes, it would just update this table. So that basically allows us to create a view and combine streams and tables inside this API. On the other side, we can actually do the same thing. So we can output data either as another stream, which goes back into that flow, which evolves our application forwards, or alternatively, we can just create a table that we might query, maybe from a GUI. So just to take a little example. Imagine we're creating a very simple service. So we have our kind of like streaming backbone here. We've got orders, customers, stocks, and payments. We've got various services contributing these data sets. We decide we're going to create an email service. And this email service is going to do a very simple job. It's going to join a stream of payments with orders and stock so that it can send an email to a customer that says, your payment has been processed, and this is the thing that you bought, and here's a picture of it and the stock description. It's a very simple idea. And we would just do this by literally spinning up a service. In this case, we've got 2 instances of them. We're going to run them fault tolerant. So if one dies, the other one will take over. It's sending out the emails. The join, so we would trigger our processing based on this stream of payments. And we would join that stream of payments every time one came in to the appropriate order and stock entry. So we get that metadata. And those would be represented as tables in this instance. So the email service drives from events, so streams, payments, orders, and stock. And then you would add your code here, which sends out the email. And then you also might create a table, if you needed to, on the backside, so that an admin GUI could view the various different emails that have been sent out. So sometimes you actually don't want to use a streaming engine. One of the main reasons you wouldn't want to use a streaming API is because you have too big a data set to fit inside your services, or alternatively because you need a richer interface. So for example, search. Let's say you want to use Elasticsearch, something like that. Something that provides you with a rich interface for queries. In which case, you just evolve your application to use a database. It's just an option. So this is kind of interesting. We have this idea of shared storage, okay, in this distributed log. So all these services are collaborating around this messaging system, and this messaging system is holding on to that data. But then we've also added this query engine, this thing that looks like a database, but it's sitting outside. It's sitting inside your service. So data storage plus query engine is like a type of database. It's a slightly strange database, but we've got this K-Streams API, which is embedding how we're going to slice and dice data inside your bounded context, inside the context of your service, but it's relying on these shared data streams that sit inside Kafka. And if we expand this further to many different services, well, now they're all collaborating over this shared set of canonical streams, but each of them is able to do its own processing. It defines what query it runs. It defines when that query changes. If you create a view which drives your GUI, you define inside your service when that's going to change. If you need to add new data, you just go back and rebuild it. So this is kind of interesting. We've kind of got this shared database. It's a slightly strange shared database, but it is a shared database nonetheless. So each service owns the processing of the data, the actual queries that are run. So this is like a database inside out. Has anyone seen Martin Kleppmann's talk, Turning the Database Inside Out? Not many. There's a reference to it at the end. It's a very good talk. I would encourage you to see it. So we have this kind of slightly kooky database where we have shared data. It's all streaming. It's all event-driven. And we're actually going to embed just the query part and the view part inside each of our services. So I put a specific slide on this because I always get this question. How do I run a query against a log? And the way you run a query against a log is by consulting an index or a view, which is something that you've created in your service, but is constantly driven and defined declaratively from those backing streams. So the index actually sits outside. You're actually pre-computing. If you've heard of event sourcing or actually CQRS, this is a very, very similar concept. So we have this idea of this database which is inside out. But we also know that microservices shouldn't share a database because they're such a rich form of coupling. But the point is that this isn't a normal database. Actually, this is a database that doesn't have shared mutable state. And it doesn't have an amplifying interface. I mean, it does have an amplifying interface because it has that query part. But that query part's embedded inside your service. But it's still tightly tied to that underlying data set. So what we're really doing here is we've reimagined what a database should be in a way that we can actually safely share it between different services in a way that services can still iterate and do their own thing. So the moral of the story, I guess, is to share a database, we should turn it inside out. So this is a slide that just kind of puts this all together to try and give you an overview of what a system like this actually looks like. It's a relatively simple example. So we have products, orders, and customers. We have, have I got a pointer here? Yeah, over here we have a schema registry. So it's always a good idea to use schemas if you're sharing data between different teams. Confluent actually provides one of these, but you can roll your own. We have an example up the top here of a very simple service. The order service is literally just a pure event-driven service. It's a very simple piece of code that just does the processing of orders and submits the result back to another topic, moving that flow forwards. Then we've got a couple of other things that are kind of interesting. We've got a search service over here. So this would actually just use connect, probably just dump the data straight into Elasticsearch. We have a pure streaming service. So this is doing something that's a little bit more advanced. So this is using stateful stream processing. And it's actually authoring state itself. So it's making use of the fact that a stream processing engine has a database inside it. And that database is actually backed up to Kafka, which means you can do effectively more complicated aggregations without needing external persistence. And then we have this UI service. So it's also event-driven. So it's being sent events by Kafka, but it's making use of this derived view. And this derived view is a bit like a materialized view in a database. So we have a query, which is the right query for this particular use case. So almost certainly something which ends up with a bag of data on the end of a customer ID. So that when the UI is booted, it just requests that bag of data for the customer. Again, we would build this. We can build this using a streaming engine, simply by applying a function which sits over those shared streams. So when we do all this, we end up with a slightly different type of architecture. And we can compare this type of architecture with the ones that we're more familiar with. So here we have 4 different architectures: a shared database, service interfaces, so that's data services, God services, event broadcast, which is the typical messaging pattern, where messages are ephemeral. Once they're sent, they're kind of deleted. And then finally, we've got the stream data platform approach, which is a retentive log with stream processing sitting on top. And then we have sort of 3 categories that we're going to use to classify these: ease of change, data accessibility, and data erosion. So shared database is really actually hard to change because it's shared mutable state. Data accessibility is great because we can just always dip into it and get things that we want. And it's also good from a data erosion perspective because we've just got one canonical source of data. Right? Can't go wrong. Service interfaces are actually pretty similar. We just added a wrapper over a database effectively. So it's easier to change because we've actually reduced some of that amplifying interface. Data accessibility is not quite as good because we're probably going to have to get that service to add new methods if we need to get more queries, so more specific data sets out of the service. And again, from a data erosion perspective, it's great, one canonical copy of data. Event broadcast, this is the traditional messaging pattern. It's very good from the perspective of ease of change. And the reason for that is that you're on a little island, you're just getting messages sent at you. But it's not so good from a data accessibility point of view, because with traditional messaging, if you weren't listening, then that data's gone. It's also not good from a data erosion perspective, because effectively you have to maintain all of these streams of data yourself over time. But when we use a stream data platform, it's easy for us to change, because the data sets are always available. From a data accessibility point of view, we can pull in any data set, any shared data set we need. And from a data erosion perspective, we're always just one step removed from that canonical set. So, for me, good architecture is actually little to do with drawing a pretty picture on a whiteboard, something that kind of looks sexy and builds you a kind of cool proof of concept. Good architecture is really about being able to evolve a system over time. That's what defines it. It's not what it looks like at the beginning. It's the transitions that you make that actually define a good architecture. So if we just use request-driven approaches, we find it's actually really hard to grow these things. And the reason is that they add too much coupling. Things become the various different services become too tightly intertwined. So we can carve these up with asynchronous flows. If we add asynchronicity, then we can have effectively islands where we isolate different services and they can change independently. So the way to do this is to embrace this data which flows between services. And actually using events is an important part of doing this, but also having somewhere for those events to live. So we want to give services their independence by having a shared data set, but not having one that has a complex amplifying interface. And we can do this by using a streaming platform, something that anyone can access, somewhere where any service can just be bootstrapped and access this data set, but still slice and dice it within its own bounded context. So you then might ask, well, how do I get there? This all sounds very good, But there's kind of like 3 stages of adoption, and I see different customers at different points in this sort of life cycle. So the simplest thing to do is literally just to do an event-driven architecture. And this is often done as a step to move you away from a legacy application. So you sort of get your data into Kafka, and then you start to build services off the side of that. So that's traditional EDA pattern. The step beyond that is then starting to think about using Kafka as a data store, somewhere where you can keep data long term. And that actually changes your operational model, much in the same way that the sort of data, the infrastructure as code people have rethought the way that they actually do deployments. With immutable infrastructure, you can play a similar trick with data. But certainly, it's something that you have a shared data set that any service can refer to. That means you can get started quickly. And then finally, you can start to build these kind of lightweight streaming functions. So these are similar to lambdas, that kind of concept on top. So we put this together, and we get a mechanism which allows us to actually evolve an architecture forwards in time. We start with something simple, but we can always add to it. And it's actually that sort of fungibility which I think really gives it its value. So there's a bunch of references here. We've got some blog posts on the Confluent site. Martin Kleppmann's done a lot of thinking around this. If you haven't read any of Pat Helen's work, I would really recommend it. Both mutability changes everything, and data on the inside, data on the outside, which I refer to a lot. He's a real thought leader here, and a couple of others. These slides will be available online. And I'm Ben Stopford. Thank you very much for spending the time listening to me. I hope it was useful. And if there are any questions, I think we have a few minutes. I know it's quite a theoretical talk, but you can ask me anything about this or Kafka, or catch me afterwards. Thank you very much.